In this video, we're testing for the convergence of an alternating series, and the first thing you always do is test for absolute convergence, because if you have that, you have ordinary convergence as well, and you can save some work. Now, this series is a little bit funky because it's not strictly alternating, and the problem here is that I have an n cubed minus 3 in the denominator, and that means when I plug in n equals 1, I get a negative number out of this. But then when I plug in n equals 2, I get a negative number again. After that, the signs are going to alternate. None of that matters for questions of convergence because it's the long-run behavior that matters when we're talking about convergence. So let's test the series of absolute values and see if that converges. If it does, then we don't even have to use the alternating series test. Again, this is not exactly the series of absolute values because the first term would be negative. So if you're really concerned about that, you could say, all right, let's just hack off the first term. And we'll just start from n equals 2. And after that, every one of these is positive. Again, it's just the long-run behavior that matters when we're asking about convergence. Now, if I look at the large n limit of this, the n is going to dominate the numerator. The n cubed dominates the denominator. And this becomes essentially 1 over n squared. So I'm going to do a limit comparison to 1 over n squared. And that's a convergent p-series. So if we find a finite number in the limit comparison, we're going to conclude that our series converges absolutely. So I take the large n limit of the terms of our series divided by the terms of the series I'm comparing to. That's the same as multiplying by the reciprocal. When I distribute the n squared in the numerator, I get n cubed plus 1 over n cubed minus 3. And again, the highest power of n dominates the numerator and dominates the denominator. So you could just cross out the 1 and 3. If you want to be a little more formal about it, you divide the top and bottom by n cubed. And that gives you 1 plus 1 over n cubed over 1 minus 3 over n cubed. And then you say that 1 over n cubed definitely goes to 0, and so does 3 over n cubed. And I end up with a 1. So because it's settled down to a finite number, I know these two series are going to share the same convergence behavior, and I go, therefore, that series converges, again with a minor adjustment to just start at n equals 2. And what this means about our original alternating series is that it's absolutely convergent. And again, a single term at the beginning can't break that. So I'm going to say that our alternating series, starting from 1, is absolutely convergent.